Hey y'all. Today we're going to be looking at how to use equilibrium constants to calculate concentrations of reactants and products at equilibrium. Let's go ahead and get started. We're going to go ahead and get started just by doing a practice problem right off the bat. So in this practice problem, I'm given a reaction, I'm given an equilibrium value, the K value, and I'm given the concentrations of some of my products and reactants at equilibrium, and I'm looking for the other. So let's go ahead and first start by writing our equilibrium expression. This is our equilibrium expression. Products over reactants raised to the power of the coefficient. So as we're solving this, one thing to keep in mind is that the water is included in this equilibrium expression. The reason water is included in the equilibrium expression is because it's a gas. If it was liquid water, then we would not include it, but in the gaseous form, we do. Also, you'll note that I'm given Kc. That's why I'm using brackets instead of parentheses. Even though this is gases, I'm actually using a unit of concentration, molarity, not a unit of pressure. If I was using pressure, I'd be using partial pressures and therefore parentheses, but in this case, I'm using molarity, so therefore I use brackets. So in this situation, we don't need to use a Rice table because of the fact that I'm given equilibrium values already. I don't need to use a Rice table to find them because I'm not given initial values. I'm already at equilibrium. I'm just looking for the unknown. In this case, that would be the concentration of the water in the air. As a result, what we're going to do is simply plug in and solve. Okay, so I'm going to find all the values that I've been given, plug them into where they belong, and then solve for the unknown, which in this case is the concentration of water. Okay, so now I solve for x and I get a concentration of 0.42 moles per liter of water. Remember, this is in gaseous form. Gases can have concentrations because they have volume, right? And the moles are variable, okay? So again, this is a really important way to solve for equilibrium values if we're already given equilibrium values of other species and the equilibrium constant, Kc in this case. All right, so let's do a second practice problem. In this situation, I'm given a K value and initial values, but I'm not given any equilibrium values. So how do I solve for it? The answer is Rice table. Let's go ahead and show you how to do this, and then I'm going to give you a chance to practice a little bit on your own after. Okay, so the first thing we need to do is write the equilibrium expression, the Kc. All right, equilibrium expression is written. Products over reactants, each raised to the coefficient. In this case, everyone's coefficient is 1. So we are all set. Now we need to figure out how to use a Rice table. In order to do this, I'm going to rewrite the equation, and then I'm going to do a Rice table underneath it. So let's start. There's my balanced equation. Now I'm going to write the initial, change, and equilibrium below it. And at this point, I'm going to plug in what I have. In this case, I have the initials of carbon monoxide and water. In Rice tables, I want to make sure I'm keeping consistent units. In this case, I'm using molarity. However, in some cases, you might use atmospheres, but I'm keeping to molarity here, okay? You might also use moles at some point or another, but like I said, right now, molarity. So if I've got 2 molar of both the carbon monoxide and water, and I'm not given how much CO2 or H2 I have, I'm going to start with those at 0. Right off the bat, we know that the reaction has to progress in the forward direction. And the reason is because we only have reactants. We don't have any products. So the carbon monoxide and hydrogen can't collide to react if they don't exist yet. So we know that the change of my reactants is going to be minus X. And the change of my products is going to be plus X. Remember the X is based off of the stoichiometry because every single one of my reactants and products has a coefficient of 1. The X's all have a coefficient of 1. If one of these was, say, 2 as its coefficient, then it would have been 2X. But in this case, it's going to be minus X, plus X, plus X. This means at equilibrium, the water and carbon monoxide are both going to equal 2 minus X. And the two products, carbon monoxide and hydrogen, are both going to equal X. What I'm now going to do is I'm going to plug into my equilibrium expression because these are equal to the equilibrium values. So my equilibrium expression is going to be X times X over 2X minus 2X. What I meant to say was it's X times X over 2 minus X times 2 minus X. So this is the same thing as X squared over 2 minus X squared. And that equals the Kc value, which is 1.56. So now we have an equation we can solve. We are looking for X because remember, what we're trying to do is fill in this rice table. We're trying to find the equilibrium values. So what I'm going to do is solve for X. Now, one thing to note is that the AP will never ask you to do a quadratic equation in a problem. However, there might be certain circumstances where you do use a quadratic, just maybe not for this class. This problem is actually solved without a quadratic using a shortcut. What I'm going to do is I'm going to take the square root of everything, okay, square root of both sides and the Kc, and as a result we get this. X over 2 minus X is equal to 1.25. Now, once we get to here, we're going to solve for the value of X, multiply both sides by 2 minus X. Make sure we cancel here and distribute here. We're going to add 1.25x to both sides. Divide both sides by 2.25, and we get x equals 1.11. Now, here's the thing. Normally you say, hey, I found x, I'm done. But in this case, you're not. Because remember, our end game was to figure out our equilibrium concentration. So now what we need to do is plug back into our rice table. So if I know x is equal to 1.11, then the concentration of CO is 2 minus 1.11, so 0.89. The concentration of H2O is 2 minus 1.11, so 0.89. The concentration of CO2 is 1.11, and the concentration of H2 is 1.11. Remember in my rice table, I used molarity the whole way. If you used another unit, make sure you're continuing that unit into your answer. But in the end, this is the way we would solve for an equilibrium amount, an equilibrium concentration, if we're given the K value, but not given any of our equilibrium values, only the initials. All right, one last practice problem. Let's do this. I'm going to have you work on this one on your own, and then when we come back, we'll work through it together. All right, the first step is going to be to write the reaction equation. NO decomposes at N2 and O2. It's not immediately balanced, so we need to make sure we put a 2 in front of the NO to balance the reaction. Now let's write the equilibrium expression using that equation. Kc is equal to products over reactants. Therefore, it's the concentration of N2 times the concentration of O2 divided by the concentration of NO squared. We need to do a rice table. Plug in what we know. So we're going to take that equation. We're going to write the initial change and equilibrium. The initial value that we know is that it's 0.2 molar for the NO. The N2 and the O2 both start at 0. The NO changes by 2x, and it's going to be minus 2x. The O2 and the N2 both go up by x. So at equilibrium, the NO is going to equal 0.2 minus 2x. The N2 and the O2 are both going to equal x. We take those equilibrium values and we plug them back into our equilibrium expression. Once we do that, we solve for x. which yet again we can simplify without having to do the quadratic. Takes everything, square root of everything, and we're going to be able to simplify it. However, if you wanted to use the quadratic and you already had a way to do it, there's no issue with it. You get the same answer. When we solve for x, we get the value of 0.099. Remember, that's x. That's not our finish line. We need to make sure we plug that back into our Rice table to find the E values for each of the things. So the concentrations of both N2 and O2 at equilibrium are 0.099. And the concentration of NO at equilibrium is 2.2 minus 2 times 0.099, which means at equilibrium, the NO's concentration is 0.002 molar. All right, that wraps up today's video. Today we looked at how to calculate equilibrium concentrations if we're given the equilibrium constant. Remember, we don't always have to use a Rice table in order to do this. In some situations, we're already given all of the equilibrium values we need. But in some cases, we need to use a Rice table to find those equilibrium values. When we do that, make sure you look to see if there's any way you can simplify the expression so that you don't have to use a quadratic equation. Sometimes you might, but most times you won't. And in terms of the tests and AP exams, you're never going to be asked to do a quadratic equation in this class. This video was written, directed, and produced by Victoria McGowan. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.